Okay, now we're going to take a look at a problem that in the past we have solved using just forces, but we were making some assumptions about what was supposed to happen. So now we're going to take a look at that same case, but assuming that we, well, not making those assumptions, I should say. So the example that we're going to do looks like this. Let me move this down just a little bit for you. There you go. Okay. And it's one that you'll recognize as being very familiar. Let's see here. Pulley. Here's the rope coming off the pulley. M. And this attaches to 2M. Okay, so you can see here what I've drawn is a pulley system. A modified Atwood's machine in which you have a pulley over which passes a string. And the string is attached to two masses, one of mass M that's hanging, one of mass 2M that's on surface. That surface is frictionless. And, well, this would be a pretty easy problem to solve back in October when we studied this. What you would do is you would make a few assumptions. You would say, okay, let's say that that pulley is massless and frictionless. Let's say that that rope is also massless and does not stretch. And you would do a free body. And actually, here, I'll work the problem for you. So the first thing you would do after you see this drawing is you would start with some free body diagrams. You would start with a free body diagram, let's say for the 2M mass. And you would put an axis on there. Let's make it our standard XY axis. And you would say something like this. Okay, well, I know that there's a force of tension to the right, T. I know that there is a force of, there is no friction actually, nothing going to the left, but there is a normal force pointing up from the surface, so that's Fn. And we also have a force of gravity downward. I'm going to call that Fg2, I suppose. And then that would be everything for that object. We could write some net force equations in the x direction. F net x equals T equals, let's see, we've got, since this is the second object, I'll call it M2 AX, so that really boils down to T equals 2M AX. And in the y direction, F net y, you have Fn minus Fg2 equals M2 AY. There is no acceleration in the y direction for this object, so that is 0. So you have Fn equals m2g, and that's Fn equals 2mg. Okay? So that's for the first object. For the second object, the hanging object, you would say, okay, here's m. We do want to line up the axis, so if the object with the mass of 2m moves to the right, and that's a positive x direction, that's going to make this object move down. To make things easier, we want to make down the positive x direction over here, and then correspondingly to the right would be the positive y direction. And again, that's just so that our directions line up, so that both objects are moving in their positive x direction. We have tension holding the object of mass m up, and we have, let's see here, the force of gravity. I'm just going to call it Fg. We have no net force in the y direction, but in the x direction, we have Fg minus T equals MAX. And so that's Mg minus T equals MAX. Now, we want to solve for the acceleration of the system and potentially also the tension. To solve for the acceleration, well, look at this. I have this solved for the tension already. I have made the assumption here that the tension in both of these strings is the same. Seems like a reasonable assumption, and that they both accelerate at the same rate, and that's definitely a true assumption. Since I already have the solve for t, I'm going to plug this in over here, and I get mg minus 2max equals max. Notice I have an m in every single term, so I'm going to cancel that out, and I'm left with g minus ax equals, or g minus 2ax equals ax. I'm going to add 2ax to the other side. I get g equals 3. Or do I? Yes. Let me just double check this real quick. Yep. G equals 3ax. I divide both sides by 3. I get ax equals g over 3. So the acceleration of this object is 1/3 the size of the acceleration due to gravity. If I want to solve for the tension, I could plug that in very easily and get T equals 2m AX is G over 3. And I get that the tension in the rope is 2mg over 3. In other words, 2/3 the weight of this, which would be mg, which makes sense because this accelerates down. There's a force of 2/3 of that pulling it up, so the acceleration must be down. Okay? And then that acceleration pulls this to the right. Now, there's nothing wrong with that analysis. That analysis is pretty good, okay? It's a good first approximation. However, there are some things that we assumed that wouldn't work in the real world, okay? I'm going to list those, and then we're going to do the analysis again, but with these factors involved. The first one, and the one that really is going to make a difference here, is that if the pulley has rotational inertia. Rotational inertia is just another word for moment of inertia. If it takes some torque to cause the pulley to rotate, in other words, if it has non-negligible mass, then you cannot just simply sum the forces. What you have to do instead is that now you have to sum the forces and sum the torques. You have to do a net torque analysis in addition to a net force analysis. And another interesting thing, something that we have been assuming all year, which maybe you thought about, maybe you haven't, is the idea that the tension here and here is the same. Okay? That doesn't really make sense if we assume that this pulley has some rotational inertia and needs to be rotated. If both of these are accelerating at the same rate, then that means that the pulley is also accelerating at the same rate, but it has what's the word? It has rotational acceleration as it spins around. Rotational acceleration means that there's a net torque involved, and if there's a net torque involved, that means the sum of the torques on that object, in this case the pulley, is not zero. This pulley has two torques on it, essentially. The torque from this string, the torque from this part of the string, the torque from this part of the string. They both act the same way away from the center of rotation, from the axis of rotation. So if they had the same force as well, then those two torques would be equal and they would balance each other out. There would be no net torque. It doesn't make any sense for this pulley to accelerate and yet have the two torques be exactly equal. So we can no longer assume that the tension is constant throughout the string. Because if it was, our pulley would not rotate. Okay, so how are we going to take care of all this? The good news is we don't really have to change either free body diagram. What we do have to change, though, just right up here, and I'm not even going to bother with the F net Y because that's not going to change at all. What we do have to change are the equations, but only very slightly. For our F net X equations, we now have to write them like this. F net X, I'm just going to put, so this is for 2m. For F net X for 2m, because we can't say that these tensions are the same, I'm just going to call this one T2 equals M2 AX. So T2 equals 2m AX. And for the net force equation for mass m, we're going to have F net X equals Fg minus T1 equals m AX. So that's mg minus T1 equals m AX. So you see the problem now is that I only have two equations, but I have three unknowns because I'm allowing for those tensions to be different. Because we are assuming, oh, I forgot the most important part. We have to actually say, okay, let's assume that in reality pulleys are not massless or frictionless. We're just going to go with the massless part right now. Let's say that this pulley has a mass of m and a radius of r. The moment of inertia equation for this pulley, which is kind of like a spinning disk if you think about it, is 1/2 mr squared, where m is the mass of the pulley and r is the radius of that pulley. Okay, so now you see, going back here, we have two equations and only three unknowns. So we can't solve this unless we have another equation that involves this. What this means is that we need to do our net torque analysis. So what I'm going to do is I'm going to draw this pulley just a little bit bigger. We're going to deal with the forces on that pulley. You can see that it's supported right here. It's probably kind of, it's got some support in the middle. So maybe there's a normal force kind of going like this, right from the middle. We know that gravity affects objects from their middle, so I'll say that this is FG P for the pulley. Oh, I need my axis, I suppose. Let's see here, axis. Since we're only looking at the rotation of the pulley, we're actually going to say, and this is going to be a little confusing, we're going to say that clockwise is positive. And the reason we're going to say clockwise is positive is because we know if we leave this system to its own devices, this M will fall, this M will slide over to the right. That will cause the pulley to rotate in a clockwise fashion. Since we said down was positive and since we said to the right was positive, we have to say clockwise is positive because those are the directions and motions that are all kind of lined up, if you will. All right, so we said clockwise is positive. That's not usually the case, but that's fine to say here. There are two other forces acting on this pulley. We just need to figure out which of them produce a torque. The force from, I get what I call this T1, acts right here. And T2, and that pulls down on the pulley. The force from T2, the tension in the upper part of the string, acts right here and it pulls to the left. T2. Now when we go to do our net torque analysis, we write down tau net equals, let's see here, the torque from, let's see here, T1. That would tend to cause it to rotate clockwise, so I'm going to call that positive because that's the direction I set. The torque from T2 would cause it to rotate counterclockwise, okay, because you're pulling it around this way. So I'm going to put a net minus sign in front of that. Torque from T2. And if you look, the torques from Fn and FGP, the normal force and the force of gravity on the pulley, should be 0 because those two forces act at the axis of rotation. A pulley spins about this central axis. Therefore, the displacement from the axis of rotation out to where those forces act is 0 meters, so the torque must be 0. So these two do not produce a torque, and these are the only forces, T1 and T2, that produce a torque. And any net torque is equal to I alpha. So, plugging in for each individual torque, I have the following. I'm going to call it R1 T1 sine theta 1 minus R2 T2 sine theta 2 equals I alpha. And now we're about to be able to substitute in a lot more. Okay, so R1 and R2, those are the displacements from the axis of rotation to where the force acts. In both those cases, that's just the radius of the pulley, which we called R. So I'm going to write R. T1, if I do some rearranging, is mg minus max. So I'm going to plug that right in. mg minus max. Let's see, minus R. T2 is already solved for us. 2max. Oh, I didn't even talk about the sine thetas. The R's in both cases seem to be perpendicular to the forces that they go along with. So both of these should be sine of 90, which is 1. So they cancel out. I, the moment of inertia of the pulley, we said is 1/2 mr squared. And alpha, we're gonna, let's see. We do have an equation for alpha that will allow us to, since we have linear accelerations here, is there any way for me to turn a linear or an angular acceleration into a linear acceleration? And there is. This alpha is actually equal to ax over r. So I've got a lot of stuff that I can do right now. Notice that I have 1/2 mr squared times ax over r. That means I have an r squared over an r. One set of those r's will cancel out, so now I don't have any fractions. And again, I have an r in every single term on both sides of the equation. That means I can totally cancel out every set of r's. And I have an m in every term in this equation. I can cancel out the m's. That leaves me with g minus ax minus 2ax equals 1/2 ax. I want to collect all my ax terms on the other side. Negative 1ax minus 2ax is negative 3ax, so it's like I'm adding 3. So if I move those to the other side, it's like I'm adding 3ax to both sides. So I have 3.5 ax, or if I wanted to write that as a fraction like I normally do, that would be 7 over 2 ax. And therefore, if I solve for the acceleration, I get 2/7 g. The acceleration of the system, if we take into account the rotational inertia of the pulley, is 2/7 g. Now think about this for a second. 2/7 g, is that bigger or smaller than g over 3? Well, g over 3 could also be written as 2g over 6, and this is 2g over 7. That's a smaller number. And that makes sense because we are now accounting for more mass, essentially. There's more inertia. It is harder to make the system move because we're accounting for the fact that this pulley has mass and therefore has rotational inertia. So it makes sense that the acceleration is not as much. Okay, so comparing those two, this makes sense. We could also solve for the rotational acceleration because alpha equals, let's see here, alpha equals ax over r, which means we have 2/7 g over r, or 2g over 7r equals alpha. We don't really have anything to compare that to from the old problem, but it is what it is. We can also solve for the tensions now. I know that T2 was equal to 2max. So that must be equal to 2m, let's see, ax is 2/7 g. So T2 is 4mg over 7. And T1 is, let's see, mg minus max. So that's mg minus m2, 2/7 g. So that means you have mg minus 2/7 of mg, or in other words, 7 over 7 mg minus 2 over 7 mg. That means this comes out to 5/7 mg, or 5 mg over 7. Look, our tensions are not the same as they were. They were both 2/3 or 2 mg over 3, 2/3 mg. Now one of them is just a little bit less, okay? Because imagine if this compares to 4 over 6 mg, that would be the same thing as this, but it's just a little bit less. This one is just a little bit more. So our tensions have worked out so that this tension is a little bit greater than this tension to assure that we have rotational acceleration right here. Very interesting. So my point with showing you this, and I'll do one more quick video on gearing in a little bit. The point with showing you all this is to show you that this first example is like a first approximation. It gets you answers that are pretty close to the right answer. This second one, however, is a little bit closer to reality. We're taking into account more things because our knowledge and understanding of physics is now more sophisticated. So these answers are a lot closer to what they would actually be in real life. Okay? Not saying this is wrong necessarily, it's just not as sophisticated of an analysis. This, on the other hand, is. I know it's tricky. I encourage you to go back and kind of look at some of this derivation and try and make some sense of it. We will practice this more. It will get easier. All we're doing is we're taking things that previously were separate and we're combining them, okay? We didn't really learn anything new here. Nothing that I said right now is anything new that you haven't studied either a long time ago or just recently, okay? So we're going to take a look at more examples like that on the homework and in class. Until then, I got one more video on gearing for you, but I'll show that to you in just a little bit.